The last section in Chapter 5 is called the inverse of a function, and by way of introduction, I'd like to talk about the movie Willy Wonka. Willy Wonka was a candy maker, and he wanted to come up with a unique way to get his chocolate bars into the hands of children throughout the world. So the output of his idea was getting normal candy to kids. And in the age of television coming into the fore, he thought about Wonkavision. How could he get candy bars to kids by Wonkavision? Well, everything, when you look at a TV screen and you see a person, they're much smaller, so he realized that he had to get a huge chocolate bar to send through Wonkavision in order that kids could see the normal and eat the normal candy. So once he came up with his idea, he realized that he had to have a huge chocolate bar, put it through the function called Wonkavision, and come up with a small candy bar. What we're going to do today with inverses is start with the output and go backwards to find the input. And from a more mathematical visual perspective, in each of these three illustrations, there are red functions graphed, and the black graph that you see is its inverse. You'll notice that they are reflections across the line y equals x, and our goal will be A, to figure out what are the equations that get us these black inverses, and we'll also ask whether or not those things are functions. As we're working through these problems, remember that x represents the input of a function and f of x, or y, is the output. So can we write a formula for the input of a function, 1/2 x minus 5? In other words, we want to not say f of x equals, we want to say x equals. So to do that, let's rewrite the equation and then do two operations. We're going to add 5 to the other side, and we're going to multiply by 2. So now instead of y equals, we have x equals. So in part B, when it asks us to find the input when the output is 14, the output is the y. We can substitute 14 for y, add them together inside the parentheses to get 19, and then multiply to figure out that the input is 38 when the output is 14. To put some context into that, the only variable in the formula for volume of a sphere is the radius. So if we change the size of the radius, we change the size of the sphere. Okay, so we know that from geometry. But also, what if we know the size of the sphere? Can we figure out the radius? So instead of having v equals, we would like to have r equals. So let's work to isolate the radius. We say that y equals the formula, and then how are we going to get r cubed by itself? We can take 4/3 and multiply by the reciprocal. Also, y is in the numerator. We can multiply by its reciprocal, and that gets us to r cubed being by itself. How do we undo a cube? We take the cube root of both sides. So now we have our formula, and the part B question is, what's the size of the radius when our volume is 50 cubic meters? Well, we insert 50 for y, and then we grab a calculator. It's easy to multiply 3 times 50, but dividing by that irrational pi is going to be a problem, and then taking the cube root. This is clearly a calculator problem. It comes out to roughly 2.29 meters. It's a good idea to note the operations that we used to find the inverse in the first example. To isolate x, we first added 5 to both sides, and we multiplied by 2. If we wanted to reverse the process, if we wanted to take x and work to solve for y, we would have to first divide both sides by 2. That's the inverse operation of multiplying. We would also have to subtract 5, which is the inverse of adding 5. So, while working to find the inverse of a function, we use inverse operations in the reverse order. Functions can go by many names. Very frequently we call them f of x, but they could be g of x, h of t, v of r. And if we ever talk about finding the inverse of a function, it's traditional to superscript a -1. You might be reminded in geometry we talked about sines, cosines, and tangents, and we also had inverse sines, inverse cosines, and we denoted those with that same -1 up superscripted. So in example 2, we're asked to take this line, f of x equals 4x minus 28, and find its inverse. So instead of having f of x equals, we want to isolate the x. To do that, we switch f of x with y, and then we switch the roles of y and x, so now x equals. We add 28 to the left, we divide by 4, and now we've isolated y. So our inverse function can be written as x plus 28 all divided by 4, or if you would prefer to see the slope-intercept form, 1/4 x plus 7. When we go to graph this, you can see that the original function in red here has this steep slope. You can also see that the inverse function has the y-intercept of 7, and I hope you can appreciate that it's a rise 1, run 4 to get to any other point on the graph. Taking a look at some of the characteristics of the original function f, it has a y-intercept of 0, -28. We see that from its original form, that constant -28. And now, when we factor the 4 out but hold on to it as our amplitude and have x minus 7, it speaks to why there's this x-intercept of 7, 0. When we look to the inverse function, we can see that there is a y-intercept of 0, 7. That's clearly on the graph. And you can take my word that there is an x-intercept at -28, 0. You can also plug in -28 for x, divide it by 4 and add 7, and see that you will come out with 0 as an answer. So do you notice that everything about x became y and everything about y became x? The y-intercept, 0, -28, switched so that the x-intercept became -28, 0. The x-intercept of 7, 0 switched so that the y-intercept became 0, 7. And look at where these red and blue graphs intersect. They are on the line y equals x. And so it should make sense that although we don't have integer values there for our coordinates of the point of intersection, 9.333 for x is the same as the y value, 9.333. We can be reminded from Algebra 1 about the vertical line test, and that is to say that we have functions if and only if no vertical line intersects the graph more than once. So looking over on the right at A and B, when we draw vertical lines, we can see that these red graphs only intersect each vertical line one time, so they're functions. What we want to now talk about the horizontal line test. That's for the sake of checking whether or not their inverse is a function, because you can remember that the inverses are going to be reflections over the line y equals x, so these functions are going to sit on their sides basically. So if we draw our inverse function, we can see that a horizontal line on the original function corresponds to a vertical line over on the inverse. Does the red function on the left pass the horizontal line test? Yes. Then that means its inverse in black over on the right is going to pass the vertical line test. For B, if we draw a horizontal line through at any point and realize that it's going to intersect our original function twice, then you can see over on the right that that black function is going to get intersected twice, and so it is not a function. It's easy enough to graph that black parabola on its side, but it's not a function. In order for us to graph that, it would require two functions. So now in example 3, we can work to find the inverse of a quadratic function, and we're going to use that horizontal line test to help us determine whether or not the inverse is a function. So we have a function in vertex form. Let's work to find its inverse by first substituting f of x with a y, and then switching the roles of x and y. We work to solve for y by subtracting 2 to the left, by multiplying by 5, by taking the square root of both sides, and finally by subtracting 6. So our inverse of the function is y equals plus or minus the square root of 5 times x minus 2 minus 6. Is this inverse a function as well? Well, algebraically, we can look up at that final step and see that we have that plus or minus, and that immediately tells us that the inverse of the original function is itself not a function. Because in order to graph it, we would have to graph y equals the positive square root of 5 times x minus 2 minus 6, and also y equals the opposite, negative radical 5 times x minus 2 minus 6. So because it takes two functions to graph the original, y equals plus or minus is not a function. It's two separate functions coupled together, but together they are not a function. Graphically, we can see the red original function and now its inverse in blue, but we are going to say that that is not a function because it doesn't pass the horizontal line test. Just real quickly, we can see, yes, it does pass the vertical line test. That's great. However, when we draw horizontal lines on our original function, they correspond to vertical lines on the inverse. Because horizontal lines pass the original parabola more than once, it means that vertical lines will pass its inverse more than once, and therefore not a function. Other things to note about these two parabolas. After we have switched x and y and found the inverse, everything about x and y switches. What do we mean by that? Well, looking at the original equation, we had the 1/5, a vertical shrink of 1/5, and now look at the last equation. Under the radical sign, we have that 5, and remember, the b value has a reciprocal nature, so that's a horizontal shrink of 1/5. They're both shrinking by 1/5, one vertically, one horizontally. That's a switch of x and y. Originally, inside the parentheses, x plus 6 was a shift to the left. Now, in our final answer, our inverse, we have minus 6 at the end. That's a vertical shift down. We think of going to the left as a negative 6 units. We think of going down as a negative 6 units. Originally, it was plus 2, which was a vertical shift up 2 units. Now, that x minus 2 at the very end means that that is going to shift horizontally to the right 2 units, both of those being positive 2. You can look up into the graph above and see that the original function has a y-intercept of 0, 9.2. Look at the x-intercept for the blue, 9.20. What was x became y, what was y became x. The original parabola has a domain from negative to positive infinity. We can plug in anything for x and add 6 and square it and multiply and add. When we look at the blue, although not much of it is shown, you get the sense that that parabola is going to go down forever and up forever. The range goes from negative to positive infinity. And finally, what was the range for the original parabola? The vertex had a low point of 2, so we go from 2 to infinity, rising. And now that parabola in blue has a far left y value of 2, and it's going to move to the right forever. So everything about the domain and range switch places. Finally, we're going to try to match the graphs on the left with their inverses on the right. And I would ask just to focus on the 4 on the left for a second and run the vertical line test. Are these all functions? Yes. Then run the horizontal line test. Do each of these pass the horizontal line test? The answer to that is yes. And so all 4 graphs over on the right are also functions. You clearly, by looking at those, can run the vertical line test and see that it works, but that is precisely because the horizontal line test worked over on the left. These aren't hard to match up, but I think it's a good opportunity to use some language that might help. When we look at the line for number 1, it looks like it has a y-intercept of 3 and a slope of 2, and there's only one line over on the right. I think we can see that there is a y-intercept of about 1.5, but we can also see that there's an x-intercept of -3, and we do still rise 1 and run 2. So I thought by putting the x plus 3, you could see how that's a horizontal shift to the left 3 units, and how that matches up with the vertical shift down 3 units for its sister over on the left. When we graph those things together, we can see how they're going to be reflections over that line, y equals x. Moving on to graph 2, we have half of a parabola. Its vertex is at -3, -1. So in vertex form, we can put that as x plus 3 squared minus 1. But because we only want the right-hand side of the vertex, we can restrict the domain to say that we only want x to be greater than, or perhaps even equal to, -3. When we look down at graph C on the right, that's going to be the inverse. And so instead of squaring, we're going to take the square root. Instead of shifting 1 unit down, we're going to shift 1 unit to the left. Instead of shifting 3 units to the left, we're going to shift 3 units down. Everything about x and y switch places. In the graph on the left, number 2, we put a restriction in so that we only had half of a parabola. But when we graph the equation for C, we're only going to get the top half because this is only the positive version. We would need plus or minus in order to get the down version. Look at both of these together, and you can see how they are a reflection across that line, y equals x. For the third, it seems like we have a cubic, and it seems like we have shifted up 2 units. So quite simply, y equals x cubed plus 2. Well, what's the inverse of cubing something? Taking the cube root. What's the inverse of shifting up 2 units? Shifting to the right 2 units. So when we look at example A over on the right, we take the cube root of x minus 2. Look at those together, and they are mirror reflections. And just like when your finger touches the mirror, it looks like its reflection is touching as well. You can see where those 2 graphs intersect the orange line. They both intersect. And obviously, graphs 4 and D will go together. It seems like we have a radical. There's a shift. Instead of having that vertex point at the origin, it is shifted over a little bit. I made it just 1/2 just to approximate, and I threw in an amplitude of 2. But if I do that, then when I come over to the graph over in D, the inverse of taking the square root is squaring, so I'm going to want something squared. If I have a vertical stretch in the left of 2, then I'm going to want a horizontal stretch of 2, and we do that with the reciprocal 1/2. And the square root function was just the positive half of the parabola. So when we come over to D, we're going to restrict our domain and say we only want to go when x is greater than 0. Thanks for watching day 1 of section 5.6, inverse of a function. Your homework will be posted, and there will be another tutorial on day 2.